Hello! In this video, we are going to prove the following theorem. Let a and b be subsets of real numbers. Let f be a function from a to the real numbers. G is a function from b to the real numbers, where the range of f is a subset of b. If f is continuous at a point c in a, and g is continuous at f of c, then the composition, g compose f, is continuous at c. Now, since the range of f is a subset of b, this is telling us that every output value of the function f will be an element of b. So if we consider any element x in a, well then f of x is an element of b. Or in other words, f of x is an element of the domain of the function g, so we can send f of x into the function g. We get an output value g of f of x. And because we can get that, that tells us we can make sense out of the composition of these two functions. Now the claim is that g compose f is continuous at c. Now before we prove that, let's first remind ourselves, by the definition of continuity, what it means for f to be continuous at c, g to be continuous at f of c, and g compose f to be continuous at c. To say f is continuous at c means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in a, if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. Similarly, to say g is continuous at f of c means for every epsilon greater than 0, there exists a delta greater than 0, such that for all y in b, if absolute value of y minus f of c is less than delta, then absolute value of g of y minus g of f of c is less than epsilon. Right? We're saying b here because the domain of the function g is b. And to say g compose f is continuous at c is pretty much the same thing as saying f is continuous at c. It's just instead of the function f, we have the function g compose f. Okay, so now let's get into proving this theorem. Now to prove g compose f is continuous at c, what that means is we're trying to prove that this third statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a delta greater than 0 such that this is true. And to do that, well, first of all, since g is continuous at f of c, this means we are given that this second statement is true. And this second statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we have in our proof. So taking epsilon to be epsilon, we have that there exists a delta greater than 0. I'll call it delta 1 instead, such that for all y in b, if absolute value of y minus f of c is less than delta 1, then absolute value of g of y minus g of f of c is less than epsilon. But then, we also know that f is continuous at c, which means we are given that this first statement is true as well. And this first statement works for every positive real number. So in particular, it must work for the positive real number delta 1. So we're going to replace this guy with delta 1. Well then in that case, there exists a delta greater than 0. Instead, I'm going to call it delta 2, such that for all x in a, if absolute value of x minus c is less than delta 2, then absolute value of f of x minus f of c is less than delta 1. Now remember, the whole goal has been to find a delta greater than 0 such that this is true. Because we're trying to prove g compose f is continuous at c. The claim is if we take delta to be delta 2, then this statement will be true. So now, to prove this statement, let's give ourselves an arbitrary element, x in a, and suppose absolute value of x minus c is less than delta 2. From here, the whole goal is to show that the absolute value of g compose f of x minus G compose f of c is less than epsilon. Now first, since x is an element of A with the property that asked value of x minus c is less than delta 2, well, that tells us x satisfies both of these conditions. So we can conclude asked value of f of x minus f of c is less than delta 1. Now let's remind ourselves, every output value of the function f is an element of B. So in particular, when we send x into the function f, the output value f of x will be an element of B. Now, replacing y here with f of x, we know that f of x is an element of B, and asked value of f of x minus f of c is less than delta 1, because that's what we have here. So this tells us that we can conclude that the asked value of g of f of x minus g of f of c is less than epsilon. But by definition of composition of functions, g of f of x is g compose f of x. G of f of c is g compose f of c. So this shows asked value of g compose f of x minus g compose f of c is less than epsilon, which is exactly what we wanted. So we have proven this statement, which means we have proven g compose f is continuous at c. And so this completes the proof. Now, a corollary of what we have just proven is the following. Let A and B be subsets of real numbers, where f is a function from A to the real numbers, g is a function from B to the real numbers, and the range of f is a subset of B. If f is continuous everywhere on A, and g is continuous everywhere on B, then the composition g compose f is continuous everywhere on A. So to prove this, well, we would like to prove g compose f is continuous everywhere on A. So what we would do is we would give ourselves an arbitrary element of A. Call it C. Well then, since f is continuous everywhere on A, then in particular f is continuous at C. Now, we know the range of f is a subset of B, so in particular, f of C must be an element of B. Since g is continuous everywhere on B, we know that g is continuous at f of C. So, since f is continuous at C and g is continuous at f of C, well then by the result that we just proved, it will follow that g compose f is continuous at C. So, if you're given an arbitrary element C and A, it will follow that g compose f is continuous at C. Since C was arbitrary, that would imply g compose f is continuous everywhere on A. So that would prove the corollary. And so yeah, that's pretty much it for this video.